Hello and welcome to this session on how to boost your ML-powered recommendation and fraud detection workloads using graph databases and graph machine learning. My name is Kevin Phillips and I'm a specialist solutions architect working for AWS in the Amazon Neptune team. Firstly, I want to make sure everyone understands what graph databases are, so I'm going to cover the fundamentals as well as the types of challenges graph databases help solve. I'm also going to talk a bit about the Amazon Neptune graph database service. Next, I'm going to dive into what machine learning using Amazon Neptune looks like and describe the workflow that enables customers to easily combine their graph data with machine learning models. I'll be demonstrating how to run the Neptune ML process using its built-in APIs, as well as how to write inference queries using the Gremlin graph query language. I'll finish off with some examples of what customers are building using Neptune ML, as well as summarizing what we covered during the session. So let's start by introducing what graph databases are. Well, graph databases are purpose-built to store and navigate relationships. They're used to model the world and how things interact with each other in a more natural way. They have advantages over relational databases for use cases like social networking, recommendation engines, and fraud detection, where you need to create relationships between data and quickly query those relationships. Now, there are a number of challenges to building these types of applications using a traditional relational database. For example, you would need multiple tables with multiple foreign keys. The SQL queries to navigate this data would require nested queries and complex joins, all of which will be hard to manage over time, and the queries will become less performant. In contrast, graph databases use the concept of nodes to represent data, represent entities, edges to represent the connections between those nodes, and properties to store data against nodes and edges. What this means is that because the edges and relationships are actually part of the data model, it means querying over them and querying between the nodes is going to be much more performant. So what are some of the technical challenges that graph databases help solve? Well, firstly, they're great if you've got data in different areas of the business or you're gathering data from different sites or locations around the world. You can use a graph database to combine this data together in different ways to satisfy different business objectives. Secondly, where you've got data that's connected but it's difficult to identify common connections or paths, you can ingest the data into your graph database and use visualization or analytical type tools to identify common connections that would have otherwise been missed. Also, if you're ever working with heterogeneous data or indeed data with complex relationships, graphs are purpose-built for this type of data. For example, if I'm trying to model out users with accounts, addresses, transactions, all of which have potentially multiple relationships with other types of data, this would be a struggle using a different type of database. With graph, I can simply add relationships between the data to build those additional connections. And finally, if you've ever tried to model data with multiple many-to-many relationships in a relational database, you'll understand that you'll need intermediary tables to extrapolate these many-to-many relationships out. With graph, you can connect any node to any other node that makes sense from your business requirements. Great, so we've learned a bit about graph databases. Now let's take a look at Amazon Neptune, our purpose-built graph database service. So Amazon Neptune is a fast, reliable, fully managed graph database service that makes it easy to build and run applications that work with highly connected datasets. Now, Amazon Neptune supports the popular graph models and graph frameworks, labeled Property Graph and W3C RDF, providing customers with the flexibility to choose either or indeed both depending on their requirements and use case. The core of Amazon Neptune is a purpose-built, high-performance graph database engine optimized for storing billions of relationships and querying the graph with millisecond latency. Amazon Neptune is highly available with read replicas, point-in-time recovery, continuous backup to Amazon S3, and data replication across availability zones. Neptune is secure with support for HTTPS encrypted client connections, as well as encryption at rest. Neptune is fully managed, so you no longer need to worry about database management tasks such as hardware provisioning, software patching, setup, configuration, or backups. And finally, Neptune also supports the Gremlin, OpenCipher, and Sparkle query languages. So depending on the type of framework that you choose, you've got the flexibility to write queries as you need. So databases, as we all know, are never just standalone. And this is a small view of how Neptune integrates with other AWS services. And there are many others, from management and operations to security and infrastructure as code. Now, the primary integration that we're going to talk about today is with Amazon SageMaker, and that's Amazon's fully managed AI and ML service. And we're going to dive further into this topic in the next section. So let's now take a look at how machine learning is applied to graph databases. So first of all, why do we actually want to use machine learning on graph data? Well, graphs and machine learning are a natural complement to one another. Graphs allow ML models to leverage the connected nature of data to provide unique and novel features based on the network structure. These features can prove highly predictive and increase the accuracy of models, especially where the connections within the data are an important predictive element. In domains such as fraud, recommendation, and many other use cases, the types of data being collected and the structure of that data evolves over time. Now, graphs allow you to efficiently model this evolution and allow you to represent this evolution in ways that increase the predictability of ML models. Now, graphs such as those used for knowledge graphs, fraud detection, or indeed product recommendations frequently contain vertices and relationships that number in the billions of objects. Now, through the use of graph and graph embeddings, this large amount of data can be efficiently represented for use by machine learning. So here's what a traditional path to building a graph machine learning solution might look like. So specialists and experts in graph databases, deep learning frameworks, and machine learning will all be required before even getting started. Data teams will need to design a mechanism to be able to export the graph data, then perform feature engineering on that data. Specialists will then need to develop the machine learning models and then manually iterate over these in order to find the best model for the data, as well as build the infrastructure to be able to support the framework. Essentially, each of the many steps of the machine learning process requires a large amount of manual work, expertise, and repetitive work to create a highly predictive model. So where does machine learning on Neptune fit in? Well, we build a service called Neptune ML to simplify the process of combining machine learning with your graph data. Now, with Neptune ML, graph developers can easily develop machine learning GNN models using the Deep Graph library. So ML developers can easily engineer features from their graph, and the infrastructure and technology to support ML model development is powered by Amazon SageMaker. What this results in is a significant reduction in the amount of effort and time needed by your development and ML ops teams. So what are some common use cases for Neptune machine learning? Well, fraud detection workloads using Neptune machine learning is a common use case. Customers want to check if transactions are potentially fraudulent in real time, or in environments such as online gaming, whether or not there is collusion between players. Product recommendations is also another use case that's driving Neptune machine learning adoption. Finding what a person might want to buy next based on their transaction history, their interests, or reviews of similar products is a common scenario. Also, using Neptune ML with identity resolution use cases provides customers who have identity graphs and customer 360 graphs to efficiently resolve and link multiple references to the same real-world entity. And finally, customers combining multiple data domains to create knowledge graphs use Neptune ML to infer connections between nodes, as well as predict the type or classification of data within their graph. Let's now take a deep dive into the Neptune ML service and how it works under the hood. So Neptune ML is API driven, and it has 4 simple steps to get you from your graph data to creating an ML model. Now, the first step is to export your data and your configuration. So a service call is made specifying the machine learning model type. So for example, link prediction or node classification, along with the model configuration parameters. Now, amongst these parameters are the number of training jobs to run, the hyperparameters used for training your ML model, and the evaluation metric used to determine model performance. Now, graph data and the model configuration parameters are then exported from your Neptune cluster to an S3 bucket. Next, we build and train our model. So from here, a set of REST service calls are made to pre-process the exported data and train the machine learning model. Neptune ML achieves this by automating the normal machine learning process of dividing data into training, into validation, and into test sets. It then uses the training data set to build the model, the validation data set to validate the model and determine which is the best model, and then estimates the model accuracy using the test data set. Now, using these steps, Neptune ML simplifies the overall model building process by automatically returning the best model possible for the configuration provided. Now, under the covers, all this processing and training is actually being handled by the Amazon SageMaker infrastructure. So after the model has actually been trained, a REST service API call is made to create a SageMaker endpoint to host the best model created from the training. The final step is to use this inference endpoint within our Gremlin or our Spark queries to infer data at runtime or at query time using the machine learning model we created. So Neptune ML utilizes graph neural networks or GNNs, as well as the deep graph learning library to provide inference on graph data. So GNNs are neural networks for processing data that can be represented as graphs. So unlike traditional neural network methods, they adapt to graph structures and provide capabilities to perform node, edge, and graph level predictions. So GNNs use a concept called node embeddings to determine how similar different objects are to each other. Now, the DGL, or Deep Graph Library, sits on top of any one of the existing deep learning frameworks, such as PyTorch, MXNet, and TensorFlow. It implements highly optimized sparse graph operators in C++ and provides really user-friendly Python APIs for GNN-related operators. So what can you do with Neptune ML? Well, Neptune ML itself provides 5 different methods of inference on your graph data. So firstly, we have node prediction, and this is split into 2 categories, node classification and node regression. Now, node classification predicts the value of a property from a list of potential values, and node regression predicts the value of a numerical property. Next, we have edge prediction, which is also split into edge classification and edge regression. Now, these work in the same way as node classification and node regression, however applied to edges. And finally, we have link prediction, which predicts the relationship between nodes within your graph. So Neptune ML supports 5 different types of prediction, which we've just seen, but what type of inferencing options do we have? Well, firstly, there's transductive inference. Now, transductive inference is essentially where you're predicting on nodes and edges that were part of the dataset used to train a data model. So when would you use transductive inference? So firstly, when you're looking to perform inference across a large area of your graph. Also, when the time to actually update your model isn't an issue. And finally, where the export process can manage the overall size of your graph. Now, next, we have inductive inference. Now, this was launched as part of the Neptune ML service earlier this year and provides the functionality to perform predictions on nodes and edges that weren't part of the original training dataset. So when would you use inductive inference? Well, when you want to infer on newly created objects and where you've already trained the ML model on representative subgraphs. Also, if your ML model will be used for a long time, why go through the time and effort to continually retrain when the fundamental structures aren't changing? So what happens under the hood when you infer on a newly created node, for example? So Neptune queries a node and its connected objects to build a subgraph. Now this subgraph is then sent to the SageMaker ML model, which is then used to perform the prediction. Now there is a slight overhead to using inductive inference due to the need to query for the subgraph. Okay, so we've learned a bit about how machine learning works with Amazon Neptune through the use of Neptune ML. Let's see now how we can apply this to a common use case such as detecting fraud within our graph data. If we take a conceptual model of the data we have, it might look something like this. So we have our user in the middle, and they're associated with an account. We have transactions that they've executed, and we also know some information or features about them, things like email address and telephone number. Now let's look how this translates into a potential graph model. Now, the things we identified in our conceptual model translate into entities or nodes within our graph model. So we'll have users, accounts, transactions, email addresses, and phone number. The relationships between these nodes are determined by how we want to access the data. So for example, email address has a relationship with user. However, we might want also to capture an email address at the time of executing a transaction. Now, this is just an example, but depending on the type of data available to you, could be used as a representative graph data model for fraud protection. Okay, so I'm now going to walk through the process of how to use a sample dataset in combination with Neptune ML to perform fraud detection. Now, here we're using the IEEE CIS dataset, which includes anonymized fraud data, which is available from Kaggle at the link shown on the slide. The dataset includes all the entities that we need for our fraud graph. However, when building your ML model, it's key to ensure you only include the data you actually need. So in this example, we're using cards, devices, transactions, and identifiers. Now, the process to identify fraud will be split into two stages. So first, we're going to identify the prediction target. So the data already contains 1.5% fraudulent labeled transactions. The fraudulent transactions in our graph are defined as those with the property name isFraud with a value of 0 or 1 attached to nodes labeled transaction. How we want to go about building our prediction target for training is to classify the node's labeled transaction with the property isFraud. The next stage will be to start the Neptune ML training process, where it will learn the patterns around the fraudulent transactions. It does this by creating subgraphs around the fraudulent transaction nodes and converting the specified properties of the surrounding graph objects into embeddings for similarity matching. The first step in our Neptune ML process is to specify the parameters for the data export and model configuration. In this example, we are showing an export and configuration for running a node classification workload. The top section of this document specifies information about the export, including the cluster information, if the cluster is IAM database authentication enabled, and if you want to use a clone of the cluster to perform the export. Clones can be set up so that the data export process does not impact the production cluster performance. The next section of the document specifies the type of machine learning tasks to be run, i.e. node classification, and the target node label and property we want to predict. In this case, it's the isFraud property of the transaction node. The final section of this document specifies details about the types of data stored in our graph and how the machine learning model should interpret that data. And this is a graphical representation of the embedding values that are generated from our machine learning model using the configuration that we specified in the export process. On the left, we can see the results relating to how the isFraud property has been predicted across the data in our ML model. The confusion matrix on the right shows a 2D representation of the node embeddings, along with the overall accuracy of our ML model. Now, once the machine learning model has been created and we've used Neptune ML to create us an endpoint to that ML model, we can start performing inference directly from within our queries. Now, in the first query, we're looking to identify whether a specific transaction node with an ID of 3001822 is fraudulent and return the isFraud property along with the ML model's confidence rating. The next query is to add the isFraud property to all transactions where it doesn't already exist and populate it with the classification value from our ML model, which will be either a 0 or 1. In both of the previous queries, we were using transductive inference, i.e. the transaction node that we were predicting on was already within our initial dataset when the model was created. So what about performing inductive inference on newly created transactions to determine if they could be fraudulent in real time? Well, first we're going to create a new transaction node and populate some default properties that align with our original dataset. We're also going to create some edges to associate it with a mobile device, a card, and identification information. Now, once we've created the new transaction node, we can start to build our real-time inference query. Here we're using the same premise as before, but this time we're supplying the ml.inductive inference parameter. Now, as previously mentioned, Neptune will calculate a subgraph of nodes and edges and properties to provide it to the ML model in order to generate a prediction. Now, by default, inductive inference queries run in a non-deterministic mode, which means Neptune builds the neighborhood randomly. When making predictions, this normal random neighborhood sampling can sometimes result in different predictions. Now, when you include the ml.deterministic parameter in an inductive inference query, the Neptune engine attempts to sample neighbors in a more deterministic way so that multiple invocations of the same query return the same results every time. However, the results can't be guaranteed to be completely deterministic. Here we have a result that specified this transaction is potentially fraud with a 0.56% confidence score. So I want to just show now as what are customers actually doing with Neptune ML. So here's an example of a customer workload that's using Neptune alongside Neptune ML to perform fraud detection in real time. Now, Kareem is a customer based in Dubai that started out as a ride-hailing platform and is now expanding its services to include delivery, payments, and more. In 2021, they had 50 million customer accounts across 100 cities in 14 countries. Now, their challenge was that fraudsters were looking to exploit and create identity fakes accounts, i.e. first-party fraud, and hijacked genuine accounts, i.e. third-party fraud. Now, in order to reduce the effect on both revenue and brand reputation, their data science and analytics integrity teams needed improved ways to detect and stop losses from fraud. So, what was their approach? They identified that they needed to be proactive rather than reactive and decided to focus on the identity of users as a starting point to detect fraud. They opted to use graph structures to map different aspects and data points of each user's identity together, and importantly, characteristics shared across the identifiers of different users, things like device ID, IP addresses, emails, and credit cards. They then employed machine learning combining data from their graph to perform node classification, which is to predict the categorical feature of a node property. In their case, it was the isFraud flag on a node. Now, the results of the original test using machine learning has shown the model to be able to predict or to correctly identify over 50% of historical fraud with an 85% precision rate. Now, work is now being done to deploy this trained model to production, allowing it to detect fraud in use cases such as when a fraudster sets up a new account or compromises an existing one. Okay, so Let's now dive into the demo where I'm going to show you how you can actually implement Neptune ML fraud detection workflow directly from within a Jupyter notebook.
For this demo, we're going to be using a Neptune notebook. If you're familiar with Jupyter notebooks, this is essentially a Jupyter notebook hosted on SageMaker that uses a Neptune-specific lifecycle configuration that enables it to connect to your Neptune database cluster. I've already got a Neptune notebook for this demo, so let's go ahead and open it. All the notebooks below the Neptune folder are part of the Neptune Workbench, an open source collection that includes examples for machine learning, visualization, and data science. So this notebook will demonstrate the Neptune ML API steps in order to export, process, train, and create an ML model based on your graph data. This is a visualization of the data that we're going to use. Fundamentally, it's an anonymized data set containing transactions, cards, devices, products, as well as a number of additional identifiers. The first step we need to do is check our Neptune database cluster is ML enabled, and then we need to load the data for it in data from S3. So Neptune ML provides a utility function to check if ML is enabled by running a status command on a connected database and checking if the Neptune _ML _enabled parameter is set to true, which it is. We can then start to load our data using the Neptune bulk load API. Now I've already done this part, so we can kind of skip this. So this is a visualization of what the graph data model looks like. Now we can see transactions associated with multiple identifiers, a card, and a device. We can then run some rudimentary queries to check if we've loaded all our data successfully. Here we're checking the number of vertices that we've loaded within our data set, and here we're checking the number of edges. Excellent. So the next steps are to export our graph data, process the data, and train our ML model. We can use the built-in utilities provided by Neptune ML to do this. So when exporting the data, we specify both the node and edge labels we want, along with, just as I've highlighted here, along with the targets of our prediction. In this case, the isFraud property on the transactions is the target that we actually want to start predicting on. Now, once we've actually exported our data, we run a data processing command to generate the training data configuration file, which stores all the details about data segregation, hyperparameter optimization, etc. And that is stored within this file here, which is also stored within our S3 bucket. And this is the Neptune ML API query to actually start the data processing. Now we can actually start using the process data to train our ML model. It's key to mention that at this stage, you can actually monitor the training data configuration JSON file if you want to provide custom values for any of the configuration parameters that SageMaker will use to train the model. Again, we use the Neptune ML functions to initiate the training job, and that's done here. So we've nearly finished using Neptune ML in the model generation process. The last step is to create an endpoint for our ML model. This is effectively the name of the model that Neptune can use within its Gremlin queries to direct ML queries to. Again, for the sake of brevity, I've pre-run this to generate an endpoint. And here's the name of our endpoint within SageMaker. So here we're going to run our first ML-based query. Now this will predict the is-fault flag for a specific transaction along with our ML model confidence score. So let's scroll down. So here we can see that, that the ML model predicts that this transaction is not fraudulent and has nearly an 81% confidence score in that. Again, we can check against our predicted fraud, the predicted fraud flag, against what the actual flag was within our original data set. If you recall from the presentation, graph neural networks use the process of converting properties into embeddings in order to perform efficient similarity searches. Now with Neptune ML, we can query those embeddings and predictions in order to visualize and plot the separation between the classes. Now to do this, so here we're importing the matplotlib function, library, the Python library, and combining it with the embeddings and predictions that we retrieved using the Neptune ML functions up here. So you can see Neptune ML get embeddings, Neptune ML get predictions, and we can use this type of code to produce an actual graph of the embeddings for a visualization. Now, our previous queries that we showed all involved data that was part of our existing training dataset. So effectively, we were predicting using transductive inference. So what if we created new data based on the same schema and wanted to predict on that? Well, we can demonstrate that here. Let's first ensure that our new transaction and our new device type doesn't exist. So we're looking for a transaction with an ID of 9999999. We'll make sure that doesn't exist, so we're deleting that. Again, we want to go down to device type, and we want to make sure that doesn't exist either. Now we're going to add our device type, which is device type of cell. And within this code, what we're doing here is we're adding the new transaction, specifying the ID of 9999999, as well as some additional properties, so all of these additional properties, to ensure it matches with the expected schema. We also add edges or relationships, and we can see these with the add E here. And these are to other nodes within our graph, as this will be representative of the data already in our model. Now notice in this query, we're passing the inductive inference parameter to Neptune ML. Now this tells Neptune to create a subgraph of this node's neighbors and send that to the ML model for similarity matching. And if we run that, you'll soon get an output, and we see that output here. So Neptune ML model has determined, or has certainly predicted, that this is not a fraudulent transaction, with a score or a confidence rating of about 56.2%. Now, in this query, in this query that we've just run, we've also specified the deterministic parameter. Now, in deterministic, by setting the deterministic parameter means that Neptune will always try and sample the same neighbors. Now we can actually remove that to tell Neptune to default to random neighbor sampling. And as you can see within this one, this query does not have the deterministic parameter. And if we were to compare, we can see that this again is predicted as false, but with a 56.1% confidence rating, whereas deterministic was a 56.2% confidence score. Now, once you've finished with this notebook, it's best practice to delete the endpoint that Neptune ML created to ensure you don't incur any unnecessary cost. With that, let's head back to the presentation for the wrap-up.
Okay, so we've covered a lot in this session, so I'd like to summarize some key points. So Neptune ML was developed to simplify the process of combining graph data with machine learning models. It uses graph neural network, or GNN technology, powered by Amazon SageMaker and the Deep Graph Learning Library. So Neptune ML supports both transductive and inductive inference, so you can predict on both data that was part of the training data set and also on newly created graph objects. Neptune ML supports 5 different types of inference: node regression and node classification, edge regression and edge classification, as well as link prediction. And you can perform query time inferences directly from within your Gremlin or Sparkle queries using ML model endpoints. And so now I'm going to share with you some resources that can get you started on your path to machine learning on graph using Amazon Neptune and Neptune ML. So first of all, our Neptune documentation pages describe in depth the service, the features, and how to optimize things like data ingestion as well as data modeling. There is also a section dedicated to Neptune ML, which includes explanations of how Neptune ML utilizes DGO and GNNs, along with a CloudFormation template that you can deploy within your own account, which sets up the supporting architecture for exporting data and training your ML model. Next is the official website for the DGL. Now this includes information on how the DGL works, tutorials to get started, and documentation on using its API. And finally, there's lots of additional resources that can help and support you on Neptune. For example, Neptune Notebooks is a collection of Jupyter notebooks containing samples for graph languages, use cases, and machine learning. There are also reference architectures you can use to help you design your optimal ingestion pipeline. And finally, there are sample applications, blogs, videos, and open source code on our developer resources page. And with that, I'd like to thank you for listening to this session.